Okay, today we're going to be looking at the geometric distribution. So let's consider rolling a dice. So we're going to roll a dice, 6-sided, and we want to think about how likely we are to get our first 6 on the first roll, or the second roll, or the third, and so on. So if you keep rolling this dice, and first time you don't get a 6, second time you don't get a 6, what's the probability, how likely are you to get it on some roll that we'll call R? So we're going to answer these questions with, so there's a constant probability. So with the case of a dice, the probability of rolling a 6 is 1 in 6, and that never changes. So the success is 1 in 6 is P. I'm going to do that actually because I want to make it generic. Is P, and a failure is 1 minus P. So the probability of a 6 first roll is going to be P, which is a success. Probability of a 6 on second roll is going to be the probability that the first roll was a fail multiplied by, so this is success, and this is fail, then success. Probability of a 6 on third roll is going to be 1 minus 2, and then it's 1 minus P, then it'll be 1 minus P, so it's 1 minus P squared, P, which is 2 fails, then a success. So what we can do is we're going to call R the number of times we roll our dice, and the probability of the X when it's R. So one roll, the probability was just P. After 2 rolls getting our 6, it was P 1 minus P. If we did 3 rolls, then we got our 6, you would have P 1 minus P squared. If we did 4 rolls before we got our 6, we'd have P, we just add another 1 minus P to this, and then that's going to be cubed, and then so on and so forth until we get to some number n. It'd be P. Now if you look here, 3 and we get a squared, 4 we get a cubed, so our 1 minus P is to the power of n minus 1. Now what we have here should start to look familiar, because what we have built here is a geometric progression. So we have here a geometric progression. When the probability is constant and the common ratio is 1 minus P. So if we were to sum all the probabilities that we have here, and we sum them to infinity, we would get, and just using the rules for geometric progression, the sum to infinity is the first term over the 1 minus the common ratio, which is the first term is P, and 1 minus the common ratio, which is 1 minus p, and that just gives us 1, because we'd end up with p over p, which is 1, which is what you would expect, because when we're doing these distributions, all the different probabilities would add up to 1. It's either a success or a failure, and the sum of probabilities is 1. So, a discrete random variable x is said to have a geometric distribution and is defined by a parameter p if the following is met. First, the repeated trials are independent the repeated trials can be infinite in number. There are just two possible outcomes for each trial. That means either a success or a fail. And the probability of a success is p and is constant. So a random variable x is a geometric possession, so we have g, we define it as p is a geometric progression with a random variable p, where p of r, so the success on trial r, is equal to p 1 minus p to the r minus 1, where r is 1, 2, 3, so on and so forth. Binomial and geometric progression distributions arise in very similar situations. The significant difference is that the number of trials in a binomial distribution is fixed from the start, and the number of successes are counted, whereas in a geometric distribution the trials are repeated as many times as is necessary until the first success occurs. So for the binomial distribution, there are n choose r ways to obtain success, to obtain r successes, sorry. For a geometric progression, distribution, sorry, there is only one way to obtain the first success of the rth trial. So let's think about the rolling of the dice. We could talk about, if you were looking at the rolling of a dice as a binomial distribution, you could have your dice and a success is a 6, and you could roll that dice, say, 100 times, and you might want to find a probability of rolling, say, 34 sixes. So in that, your n is 100 because you've rolled it 100 times, but you've had 34 successes. In the geometric progression, the difference is you're looking at the probability of when you can get that first success. So you are going to keep rolling and keep rolling. You could roll that dice forever and never roll a 6. It's highly, highly, highly improbable, but it's not impossible. So you'd be thinking, well, what is the probability that, say, on the 100th roll is when we get our first 6? And that's the difference between when you would use a binomial distribution and a geometric distribution. So the geometric is when you're just thinking about that first time that you get your success. But a situation, you could, depending on the number of trials and the number of successes you're looking at it, something that you use a geometric distribution could then be used again. That same situation, you could then analyse it using a binomial distribution, because you're then looking at a number of successes over n number of trials. I hope that is clear. Let's do some examples and hopefully it'll start to become a bit more clear. So, repeated independent trials are carried out in which the probability of success is 0.66. Find the following probabilities. Find the probabilities that the first success occurs on the third trial, be on or before the second, or after the third. So p at x equals 3 is going to be equal to p 1 minus p to the 2, because 2 is 3 minus 1 is 2, so that's going to be 0.66. Oh, it's meant to be a 1. Oh, there's a 1 there. I've drawn it really nicely. 1 minus 0.66 to the power 2, and working all that, you get 0.0763. Now, on or before. So, on or before the second trial means that x must be less than or equal to 2. So we have to take the probability of x equals 1 and add that to the probability that x equals 2. So we'll have p plus p1 minus p to the power 1. So that's going to be 0.66 plus 0.66, 1 minus 0.66. That's not meant to be there. Working all that out, you get 0.884. Finally, we want the probability that x is greater than 3. So when the probability of x is greater than 3, that means that is all the other probabilities, but not minus the probability that it was on the first trial or the probability it was on the second trial. So it's going to be 1 minus the probability of x being less than or equal to 3. So we've got 1 minus the probability of x equals 1 plus the probability of x equals 2 plus the probability of x equals 3. Now we already have, so it's going to be 1 minus p plus p1 minus p plus p1 minus p squared. I'm not going to write the numbers in there because it's a bit redundant. So slotting in all your p's, you'll get 0.0393. Now, we can see from that question there, let me just bring those back up, that we can have probabilities that involve inequalities. And these can be found as a summation for small values of r. However, if we've got a large value of r, you don't really want to be building this huge, big geometric progression. It's really quite, it's just time consuming. So what we can see is the probability that x is less than or equal to r equals the probability of success on one of the first R trials is 1 minus the probability of a failure on the first R trials. So I'll write this out more neatly in a minute. Then P, if x is greater than R, that's the probability of success after the rth trial. So probability of a failure on the first trial. So for when x is a geometric progression of with probability p, and let's say q is the probability of a failure, the probability that a trial occurs on one of the first trials before R, or on R, is equal to 1 minus Q raised to R. And the probability that X happens after some Rth trial is just the probability of a failure raised to the power R. And this is something that you need to be able to pull out and just be able to use. We're going to look at a couple of examples using this. So in a country, 18% of adults wear contact lenses. Oops. Adults are randomly selected and interviewed one at a time. Find the probability that the first adult wears contacts if A, one of the first 15 interviewed or B, not one of the first 9 interviewed. So the probability, so one of the first 15 means the probability that X is going to be either less than or equal to, because it can be the 15th person interviewed. And we know from just now that that's going to be given as 1 minus Q to the R, which is 1 minus, so Q is 1 minus P, and so that's going to be 0.82, and that is 0.82 to the 15th, and that gives us 0.949. And then not one of the 15, so P X is going to be greater than 9, so Q to the 9 is going to give us 0.82 to the power 9, and that comes out 0.168. One more question. So a coin is biased such that the probability of obtaining heads with each toss is equal to 5/11. The coin is tossed until the first head is obtained. Find the probability that the coin is tossed at least 6 times and B, fewer than 8 times. So our Q is 1 minus P, so that's going to be 6/11. So probability at least 6 times, so it's going to be X is going to be greater than or equal to 6, which X, if it let X represent the number of times that the cost is tossed, so the probability is going to be the same as P of X equal to 5. So that's Q to the power 5, which is 6/11 to the power 5, and that is 0.0483. And then the probability of fewer than 8 times, that's not an S, is it? So X is less than 8, so that's going to be equal to the probability of X being less than or equal to 7, which is 1 minus Q squared, not Q squared, sorry, Q to the power 7. So that's 1 minus 6/11 to the power 7, which is 0.986, sorry. I picked the wrong number. So I hope that helps.